Hello. In a previous video, we talked about the spectral theorem, which says that whenever you have a symmetric matrix, it has the form Q lambda Q inverse, where lambda is a diagonal matrix consisting of the eigenvalues of the matrix, and Q is orthogonal. And we're going to use that to study something called quadratic forms. So a quadratic form is a function, so let's give the definition. A quadratic form is an expression say f of x1 through xn given by f of x1 through xn equals what you get when you take the vector x1 to xn as a row vector or a 1 by n matrix, and then times a symmetric matrix A, and then times the transpose of that vector, x1 through xn. So, where A is an n by n symmetric matrix. That's one way to define a quadratic form. So let's look at an example. Well, let's say that you have n equals 1. If n equals 1, then you just have kind of one variable, and you just have something like x. So your A, your matrix, is just going to be this 1 by 1 matrix. So it's going to be x times A times x, and then that's just going to be ax squared. Right? So quadratic forms in one variable are just ax squared for different a's. All right, there's not much to say about that. Now let's look at n equals 2. And let's say that A is this matrix 2, 0, 0, negative 3. Well, in this case, we have x1 and x2. So I'll just use x and y just to make it a little easier. So you have this times A times this vector xy. So this is the same as, well, if you multiply this first, you're going to get xy times this vector 2x negative 3y. And that's just the dot product of these two vectors. You get 2x squared minus 3y squared. Okay, so 2x squared minus 3y squared is an example of a quadratic form. And you can see in general, when you have a diagonal matrix, x1 to xn times this diagonal matrix, lambda 1 to lambda n, x1 to xn, when you multiply it out, you're going to get lambda 1 x1 squared plus dot 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 plus lambda n xn squared. So that's an example, that's a more general example of a quadratic form. Just some constant times x1 squared plus another constant times x2 squared all the way to a constant times xn squared. And that's the quadratic form you get if A is a diagonal matrix. But of course you can have a symmetric matrix that's not diagonal. So for instance, let's say that you had, let's just go back to n equals 2. So I'll use x and y. If you had a symmetric matrix like 2, 1, 1, 3, if you did that, then you're going to get x, y times 2x plus y, x plus 3y. And then when you multiply it out, when you do the dot product, you're going to get x times 2x plus y plus y times x plus 3y. And now you're going to have to simplify this a bit. So you distribute the x across, you get 2x squared plus xy, and then plus yx. Well, y times x is obviously the same as x times y. And then you're going to get 3 times y squared. And now you can add the xy terms together, so you get 2x squared plus 2xy plus 3y squared. Okay. So that's another quadratic form. And actually, you can get any quadratic form of the form. So if you had ax squared plus bxy plus cy squared, you can get this by doing xy times this matrix A, B over 2, B over 2, C times xy. So a quadratic form in two variables is going to be like this. So that's the general, this thing is the general quadratic form, the general form of a quadratic form, if you will, general quadratic form in two variables. And notice that if you look at the degree of these terms, you have an x squared, which is degree 2. X times y is, well, x has degree 1, y has degree 1, and then y squared is degree 2. So you can think of a quadratic form in two variables as a sum of degree 2 terms. So sum of degree 2 terms. And you can have quadratic forms in three variables. So quadratic form in three variables, you're going to have ax cubed, and then x times y squared, and x squared times y, and y cubed. You're going to have those degree 3 terms. So we can think of these quadratic forms as functions of x and y. So can view quadratic forms as functions of several variables. In this video, we're just going to stick to functions of two variables. So for now, we'll just stick to the case of n equals 2. To the case of n equals 2. In that case, you have something like f of xy equals a times x squared plus b times xy plus c times y squared. And the question that we want to address is what does the graph of this look like? So you have this function, and then the question is, what does the graph of f look like? So remember what you're doing when you're taking the graph of a function f, what that is you're looking at all the points in three-dimensional space of the form x comma y comma f of xy. That's what the graph of f is. So this is a subset of R3, right? It's a subset of three-dimensional space. Now let's look at an example. Well, it's going to depend on your matrix A, right? So the question is really, how does the matrix A affect the graph of this quadratic form? Well, in the case where A was this matrix 2, 3, this diagonal matrix, then you're going to get f of xy is equal to 2x squared plus 3y squared. Now let's think about what happens if you graph this. So let's just call this z. What happens if you graph z equals 2x squared plus 3y squared? What shape is that? Well, you're going to have something like this. Here's the x-axis, y-axis, and z-axis. And one way to get a handle on this function is to look at cross-sections. So for instance, let's say you look at the cross-section with this plane where y is equal to 0. If you set y equal to 0 here, right, then you're just going to get z equals 2x squared. So what that means is, if you restrict to where y is equal to 0 on the xy plane, so that's let's see, y is equal to 0 is here. It's the x-axis. The graph is going to be z equals 2x squared above that axis, or above or below that axis. So what's going to happen is you're going to get this parabola 2x squared, like this. I'll do it with this color. It's going to look like that. Okay, let me draw a side view. So you can have something like the z-axis like this, the x-axis like this, and then the y-axis. So here's the negative y values, and here's the positive y values. Okay, and here's the negative z values, positive z values, negative x values here. When you just look at this plane, the xz plane, you're going to get the parabola z equals 2x squared. So it's going to look like this. Okay. And also, if you set x equal to 0, you're going to get, so now your x is equal to 0, you get z equals 3y squared. So let's see if we can draw that. Well, it's natural in this view to draw z equals 3y squared because you have this yz plane like this. So you're going to get 3y squared, like this. And so the vertical cross sections are going to be parabolas. Right? The vertical cross sections are these parabolas. And what the graph of this function is going to look like is this bowl shape. It's going to be like this bowl, where it's, let's see, this one was z equals 2x squared. This one was z equals to 3y squared. So when you view it from the perspective of the xz plane, it's the parabola you get is going to be wider on this side, whereas if you look at it from the perspective of the zy plane or the yz plane, that's going to be a steeper parabola. So it's like a bowl, but then when you rotate it, on one side it's going to be steeper than on the other side. Okay. It's not completely symmetrical. The one way of thinking about it is that the horizontal cross sections are going to be an ellipse instead of circles. But anyway, for the purpose of this video, we're not going to get too much into that. That's something that you think more about in multivariable calculus. So you get this bowl-like shape, and this point 0, 0 we see is a minimum, right? It's a minimum of the graph of this function. That's in the case where A is this matrix, 2, 3. This diagonal matrix. Let's take a look at another diagonal matrix where you take A to be -2, -3, this diagonal matrix. Well, in this case, the quadratic form is f of xy equals -2x squared minus 3y squared. And that's just, you factor out the -1 and you get 2x squared plus 3y squared inside. So this is z equals negative what we had before. So what can you do with the graph of this function before to get this new graph? You just flip it about the xy plane, right? You just make all the, you multiply all the z values by -1, and so what you end up getting is this bowl. Okay, the more technical term is a paraboloid, but okay, let's just call it a bowl. It's this bowl that's like this. And notice that 0, 0 is a maximum. It's actually where the highest point occurs. Right? The biggest value here, f of 0, 0 is equal to 0. That's the biggest value of z. In this case, 0 is the lowest value of z. F of 0, 0 is equal to 0. Now let's look at an example where one of the diagonal entries is positive and one is negative. So let's say that A is this matrix, 2, 0, 0, -3. So in this case, you have one positive eigenvalue and one negative eigenvalue. Well, in this case, your f of xy is equal to 2x squared minus 3y squared. Okay. In this case, if you look at the cross section again, so let's just call this z. If x is equal to 0, you get z equals -3y squared. And if you set y equal to 0, you get z equals 2x squared. So what that means in terms of the graph is when you look at it from the perspective of the xz plane, okay, that's when y is equal to 0, you get this parabola 2x squared. So it's like this. But if you look at it from the perspective of the yz plane, when x is 0, so positive y is that direction, z is this direction, then your positive x direction will be this way. Then you're going to get -3y squared, which is like this. Sorry, this first parabola is supposed to look symmetric. It's supposed to be like, okay. So it's this, you get this weird shape if you imagine graphing the whole thing where from one perspective it looks like a upward pointing parabola, and then when you rotate it you get a downward pointing parabola. And it ends up looking, if we try to put the pieces together, so here's the x-axis, y-axis, z-axis. From the perspective of the yz plane, it's this negative parabola. So it's like this. But then from the perspective of the xz plane, it looks like this. And I don't have a good graph of this, but it looks like, if you've ever seen a Pringle chip, it sort of looks like a Pringle chip when you graph the whole thing. Okay, does this help? Something like this? I don't know if that helps. But the graph of it looks like it's supposed to look like a Pringle chip. A Pringle. And the point the point 0, 0, this is called a saddle point. And what that means to be a saddle point is in the immediate vicinity. So if you just look a little bit around the point 0, 0, in the immediate vicinity, there are points xy where f of xy is greater than f of 0, 0. So what it means for 0, 0 to be a saddle point means that there are points xy in the immediate vicinity of 0, 0. There are points xy where f of xy is greater than f of 0, 0, and points xy where f of xy is less than f of 0, 0. So this point 0, 0 is in some sense a critical point. It's a special point, but it's a saddle point. It's neither a local max, it's not a maximum or a minimum. Okay. So I think this video was long enough. So I think I'm going to make a separate video. So let's just, for the other topics. So let's just review what we did. We defined quadratic forms. We looked at some examples of quadratic forms. And then we started looking more closely at quadratic forms in two variables. And we saw that when you have a quadratic form in two variables, the point 0, 0 can be a local, it can be a maximum point if, okay, that was the second example, or it could be a minimum point, or it could be a saddle point. And notice that it depends on, well, in this case, we only looked at diagonal matrices. But in this case, you have the eigenvalues, okay? For the saddle point, you have one positive eigenvalue and one negative eigenvalue. For this example, where you have a maximum at 0, 0, you have both negative eigenvalues only. And then in the first example, in this matrix, you had both positive eigenvalues. Both of the eigenvalues are positive. And in the next video, we'll look at symmetric matrices that are not diagonal matrices. And we'll see how we can use the spectral theorem to understand the quadratic forms corresponding to those symmetric matrices. Thanks for watching.